Well, hi everybody. We're going to have a really jolly good look at some more integral calculus in this session, and we're going to look at one of the star attractions of integral calculus, which is the definite integral. Now, we did start to look at the definite integral a few sessions ago when I was introducing the very first session when I was introducing integral calculus and we were doing approximations of areas under curves. So I'm just going to revisit that so that we'll sort of keep a more coherent thread together as to what we're doing, okay? Now, we talked about in that session about the left-hand estimate for areas under curves, and we were looking at this procedure where we were dividing up the function or the area under the curve of the function into a whole series of little rectangles. And in this particular technique, the left-hand estimate, we were drawing rectangles so that the left-hand side of the right angle, the y value, coincided with the left-hand top of the rectangle. And in that instance, we can see we added up all those rectangles like that, and we said that that really meant that the area was the left hand, for that first rectangle, the left hand y value, which would have been y when x was 2, times the width, which we call delta x, plus all the rest of them, all the left hand side y values times the delta x's or the widths, and that came to the equivalent of the sum of all the left hand sides of the y values times the delta x's, and that comes to whatever it comes to, and it's an overestimate in this case, isn't it? You can see the little bits sticking out above the curve of the function, and all those little bits there that I've just coloured in are the bits that overestimate the area. Okay, so it's not perfect, but it gets better when you basically make the rectangles thinner, as we'll see over the screen. Now, in this instance, using the left-hand estimate technique, we can see that we haven't got an overestimate anymore for a curve that curves concave upwards, like that one does. We can see that we've got an underestimate, haven't we? And that's the underestimate. And in the graph below, you can see that by making the rectangles skinnier, you can basically make the whole estimate of the area more accurate. So that's what you do there. So isn't that great? And there is that's the underestimate in that case, but it's not as bad as the underestimate in the graph above because we made the rectangles thinner. Yes, less width means more accuracy but more calculations. Yuck. So life's all full of compromise, isn't it? But don't worry, we don't have to do this much more. We're going to get the exact technique happening. And now, just to be, for the sake of completion, we'll go through the right-hand estimate, which means that we now draw rectangles so that the right-hand height of the rectangle coincides with the curve. Okay? In that case, we're going to add up all these areas where the right-hand side of the rectangle butts straight onto the corner butts onto the actual curve itself. Okay? That's an underestimate, isn't it? And that area is equal to the sum of all the right-hand side y values times the widths, which are the delta x's, and that's an underestimate, isn't it? Because you can see all the little gaps under the curve at the top of those rectangles which haven't been counted, and that's them. And as I said last time when we did this presentation a few sessions ago, that in this instance a right-hand estimate for a concave up curve is an overestimate, the opposite to what the left-hand estimate was, and that's the overestimate, and we can basically lessen the severity of our overestimate by making the rectangles skinnier, and that's what we were doing, wasn't it? Remember? Yeah, so less width means more accuracy but more calculations. And then we talked about the definite integral. Now we're starting to get into the stuff that we want to do today. The definite integral, I said, was the type of situation where we make delta x approaching 0, which means you get infinitely many rectangles but infinitely many calculations, which you don't want. but it's completely accurate, okay? Completely accurate. Fear not, we don't have to do infinitely many calculations, so the rest of your life doesn't need to flash between your eyes. It's okay, okay? Just settle down, have a chill pill. And we said that the limit of that Greek capital sigma means the sum of. So the limit of the sum of all those rectangles, their y values times their delta x widths, where you go from A as a starting point in terms of your x right up to B. The limit of all that as delta x approaches 0 is called yes, it's called that thing, and that's the definite integral, okay, from A to B. And as I said, that's the exact area from x is A till x is B. Now that's the Leibniz notation, as I was explaining to you before, and I've dug out a picture of said Leibniz this time. The S stands for lazy sum. Yeah, that thing, it's an S, that weird looking thing. It looks like a stretched S, okay? It stands for the sum of all those little rectangles. And I never ever want you to forget that you're adding up rectangles when you're doing this stuff, because if you don't forget, you'll be okay. Here he is, 1646 to 1716, and we've got Mr. Gottfried Wilhelm von Leibniz. Woohoo! He was a German mathematician and philosopher, and he occupies a prominent place in the history of mathematics and the history of philosophy. So, he apparently developed I won't go on, but he apparently developed some of the infinitesimal ideas of calculus independently of Isaac Newton. So there you go. There's no flies on the Germans, eh? So, there you go. Let's go. Off we go, and now we have to talk about something which is extremely important if we're going to get this whole definite integral thing and how to do it properly. A lot of students don't know how to do it properly, but you will when you're finished with this session. Now, integrals are signed areas. They have a sign. They have a plus and they can have a minus. So this is extremely important. They're not just an area. In fact, the word area means something completely different. It just means an unsigned area. Okay, it just means some land, if you like, some real estate, but it doesn't mean it's got a plus or a minus. So we'll talk about that later. Now, consider moving along a number line. Okay, now we're going to do this, and I'm going to get this is in order for me to explain this whole signed area thing. Okay, now we're going to go from plus 2 to negative 3 along an x number line. All right, now let's draw the number line in, and now there it is, and we're going to go from there, which is plus 2, to there, which is minus 3. Now how far am I going to go in terms of the sign and the distance? Now I'll give you a moment to think. Made up your mind? Right. Well, if the sign is important, which believe you me it is, we are going from plus 2 to negative 3. And what I'm saying is the distance travelled is the destination point minus the starting point, right? That's what you need to keep in mind. That's equal to negative 3 take positive 2. And that, ladies and gentlemen, is negative 5 units. And you can see that it's negative 5 units because you can see it's going in the negative direction. The movement from the starting point was in the negative direction to get to the destination, so the distance was negative. Okay? Now, let's talk some more about this. We're going to do another one. We're going to go from minus 2 to plus 4 this time. Okay? Now, let's do it all again. It's very important. Okay, there's our number line, and we're going to go from there to there. Now, come on, you think about it. What is the sign and what is the distance? Okay, good. We're going from there up to there, and the distance moved is the destination point minus the starting point, yes, which is going to be plus 4 take away negative 2, which comes to plus 6 units. That is that the movement from the starting point was in the positive direction. Now, I want you to get that very, very clear, okay? Therefore, the distance was positive, okay? All right, let's go. Now, what I'm saying is that integrals also have signed widths and signed heights for the rectangles which you're calculating the areas of. That is crucially important, okay? Now, therefore, what I'm saying is that integrals are signed areas. They're not just numbers, they are signed areas. Okay, so let's just have a look at this excruciatingly interesting example, which I find very, very fascinating. Hope you do too. We're looking at the integral of the function y equals x plus 1 with respect to x from x is negative 3 up to x is positive 2. Negative 3 is our starting point, positive 2 is our finishing point, right? Now we'll just fill in some of the details on this graph before we get too carried away. Look at that, the wonders of technology. Now what I'm going to do is, because we're looking at areas, I'm just going to make it a bit clearer what we're trying to do here. Put some dotted lines, and I'll call the area of the bit of the graph which is above the x-axis, that is from minus 1, x is minus 1 up to x is plus 2, I'll call that area 1, right? The area for the bit of the graph which is under the x-axis, that is from negative 3x to negative 1x, I'm going to call that area 2. And we are going to have some fun calculating these areas, right? Now the first thing we'll do is we'll just work out the unsigned areas, just the values, the numbers, okay? As if we were doing areas of triangles. Okay, now area 1, come on, have a look. What's the base? What's the height? Because that's how we're going to work it out. Okay, just as a geometrical exercise. Okay, this is why it's so much fun. So the base looks to me like it's 3, 3, isn't it? And the height, oh, the height's 3 as well. Blow me down. So therefore, that's going to be 3 by 3 over 2, because it's space times height over 2, which gets me 9 over 2 units. Now, I'm not considering whether they're plus units or minus units. I'm doing an unsigned area. You get it? Now, let's do area 2 now. Okay, so that looks like it's a 2 by 2, base 2, height 2. I'm not doing the minus, I'm just doing the lengths, like an area of a triangle, and I get 2 square units, don't I? Alright, now let's add those up. We get the total unsigned area. Unsigned would be A1, 9 over 2, plus A2, 2, which gets me 6.5, and that's 13 over 2, right? Put a box around that. It's, oh no, I didn't, oh, sorry. Oh, now, what am I getting so carried away here? So therefore, okay, now, I just want to work out with you, just for the sake of, because I know what's going to happen, I'm going to work out A1 minus A2, because it'll be a true wonder of nature when you see what's going to happen. Watch this. 9 over 2 minus 2, which is 4.5 minus 2, which gets me 2.5, or 5 over 2. Now, look what I'm doing, ladies and gentlemen. I'm working out the algebraic way of doing a definite integral. Now, what do you think this is going to come out to be? What do you think? It's very, very interesting. Now, okay, so what we've said is there, the antiderivative of x plus 1 is half of x squared plus x plus c, from minus 3 to plus 2. Now, how you do these things is you just then work out the whole thing with x substituted for 2, it's 2 substituted for x, I mean, and then you subtract the whole thing worked out with x as negative 3. That's how you do a definite integral. So come on, we'll do it. Look at that. Ain't it marvellous? So that's the first one with 2 substituted in. And now we're going to do the one with minus 3, subtracting the one with minus 3 substituted in. Now, what do you notice? I'll clean it up a bit. What do you notice about the c's? Of course you do. They cancel out. they cancel out. So when you're doing definite integrals, ladies and gentlemen, you don't have to worry about Mr. C, okay? He's just an irrelevance, okay? So, what are we going to get? The C's cancel out? Yes, so don't worry about C when you're doing definite integrals. You don't even have to put it in. In fact, that line, 1, 2, 3, 4 lines above where I just straight under the integral expression that I was trying to work out, actually I put that C in just to show you, but you don't have to put that in. You don't have to put it in, okay? And you'll see later on I don't bother. Okay, that comes to 5/2. Now, look at, isn't that interesting? The signed area, e.g. the integral, comes out to be the same as A1 minus A2 over the right-hand side. It does not equal the sum of those areas, which was 13/2. It's equal to 1 minus the other. It's A1 minus A2. Now, you see how exciting this is. So the total signed area is 5/2, which is not 13/2, and the question for you and me is why? Why, oh why, oh why? Now, I'm going to show you why. So let's fasten your seatbelts and we'll go onto another screen and you'll see the whole thing unfold like a miraculous, wonderful story. Now, there is my graph in super enlarged mode. Look at that. Now, stay with us because you're going to be very, very amazed. First of all, we're saying, okay, the signed area, or the integral, for minus 3 to plus 2. Now, let's just work out what our number line's doing. We're going from x is minus 3 to x is plus 2. Now, that is a positive direction. Do you understand that? It's a positive direction. So therefore, all of our little widths of our rectangles are going to be positive ones. Okay? Positive direction. That's really important for you to get that clear in your mind. Okay? Now, let's have a look at the height of the rectangles in the section of the graph which is under the x-axis, right? We're going to look at actually the widths and the heights. So now there's the width, there's my delta x, okay? That is positive, isn't it? We just explained that. Now what about the height? What do you think the height is? What is the y value, in other words, relative to where y is 0, which is what we're doing in this case, okay? For that height, it's a negative height, isn't it? Isn't it? Of course it is. It's a negative height. So therefore, what is the area going to do? The signed area, the height times the width, is going to be a negative height times a positive width, which is going to get me negative. Thank you, Mr. Box. Negative. So the signed area for that section of the graph under the x-axis is negative. Okay, now let's do the same exercise over the other side for the part of the graph which is above the x-axis, right? There's my rectangle. Now what about my width? Well, of course it's positive, we explained, because we're going from a lower x value to a higher x value in terms of the direction we're moving in the x, yeah? Now the height, what about the height? Yes, that's positive, and the height is positive. It's positive, yes? So therefore, what are we going to say about our area, our signed area? We're saying that our signed area is the height times the width, which is a positive times a positive, which gets me a positive. Mr. Box. Oh, Mr. Box went on strike. Oh dear, Mr. Box. You need to get your act together. Now, where was I? Oh yes, now, over in the purple on the right and the left-hand side, I'm saying now, therefore, the signed area between -3 and -1, which is the bit under the x-axis, if you worked it all out, guys, it would actually, I haven't got room to work it all out there properly, but if you did it the way I showed you, it would come out to be -2. So ain't that interesting? You see, the area, just the length, the triangular area, base times height over 2, comes to 2. But the signed area is -2, okay? Oh, thank you, Mr. Box. You've redeemed yourself again. So there you are. Now, Okay, the plot thickens. Now we're going to do the same thing for the right-hand side, okay? The signed area, in terms of my algebraic technique this time, is going to get me the same calculation done over a different domain, and that's going to get me 9/2. Didn't have time to work it all out systematically, but you get the idea and you know how to do it, and that's 9/2. Thank you again, Mr. Box. So therefore, now, are you getting what's going on here? So if I worked out the signed area straight from one extreme at -3 to the other extreme at +2, talking about x, what's going to happen is you're going to get 9/2 for the right hand side, or the bit of the graph that's above the x-axis, and -2 for the bit that's under the x-axis, and part of one bit is going to partially cancel out the other because they have signs, you see? So there it goes. That's what I was trying to explain to you. So therefore that last little bit there in the purple, just near the x-axis x sign, gets you, going from one extreme to the other, is going to get you 9/2 minus 2, which is going to get you 5/2. Thank you, Mr. Box. Now, do you get it? That's the way you need to understand this stuff, okay? That's the way you need to understand it. Now, here's a little question for you guys. Think about this. What about if I did the integral, this time, the same function, but what about if I started at +2 and finished at -3? What would my answer be for the overall integral? What would the answer be? Well, the answer, my friends, is it would be -5/2, because you're going in a negative x direction. So it basically reverses the sign of each of those signed areas, okay? That's what it does. Ain't it exciting? So therefore what we're saying is that the integral of f of x dx from a to b is the net signed area between f of x and the x-axis, between x is a and x is b. And the area as such, if you just talk about area, which questions, the textbook questions and the exam questions will ask you, if they just say what is the area, they're talking about the unsigned area. They're not even talking about pluses or minuses, they're just talking about the amount of land, if you like. Okay, the area, like the geometrical area, is all added up without any pluses or minuses or anything. So that's what they mean. So you've got to get that straight too. There's a difference between the integral, which is a signed area, and just area, which has no sign, okay? And there's no cancellation, no net at all in that stuff. So it's a sum of the unsigned areas, okay? Alright, now we're going to do properties of the definite integral. Okay, now number one, what are we saying there? We're saying that the f of x dx from a to a, well, that means it's got no width at all. That must be 0. Does that make sense? Because you think of rectangles, we ain't got no rectangles, guys, if we're not going from a to anywhere. That's why that's 0. Number two, now what are they saying there? Oh, look over the right-hand side. See how C is bigger than A, but at the same time C is less than B? Well, what they're saying there, if you look at that closely, they're saying that the integral from all the way from A to B is the, look at the right-hand side term after the equal sign. That's from A to C, that's like an intermediate point, and then add on the left-hand side just after the equal sign from C to B. Okay, so it's, yeah, I mean, I think that's pretty obvious, don't you think? It's a combination of two areas, yeah. All right, let's do number 3. Now they're saying the integral of k times f of x dx from a to b is equal to, put the k outside the left-hand side of the integral sign, because you don't integrate constants, guys. A constant can just float around, go wherever it likes. It doesn't have to be integrated. Okay, that's very important. Now, what's number 4 saying? I'm trying to read it. Oh, look, they're just saying here that, okay, if you had the integral of, say, f of x plus g of x with respect to x from a to b, you can split the functions and make two integrals out of it. You could make it f of x from a to b plus g of x with respect to x from a to b. That's all they're saying there. So you can do that too, okay? Oh, goodness, this stuff's dry, isn't it? Where am I? I don't know. Oh no, number 5, no problem. F of x dx, the integral of f of x dx from a to b is minus the same integral from b to a, okay? That's what I was just saying in the previous screen when I was talking about reversing the direction of x. That's what it does. It reverses the signed areas, so the whole thing becomes minus. Okay, goodness. Right, are you still with us? Well, I hope so. Now we're going to do a few now. Thank goodness we get some examples to do now. Right, evaluate the definite integral x with respect to x from 1 to 2. That's a nice easy one, isn't it? Just to sort of get us going. So, right, let's see. That just gets you a half x squared from 1 to 2. And you notice I didn't put a c in there anywhere. No c's inside here, guys. So that comes to that expression there, which gets us that, which gets us 3 over 2, and Mr. Box. Thank you, Mr. Box. Now, yeah, and another little thing to throw in for you too, you know, if you're just harking back to the indefinite integrals, if they say they want the antiderivative, you always have to put a c in. But if they just say they want an antiderivative, that just means a specific one, in which case you're allowed to leave the c off, okay? But make sure you put that c in if they ask you for the antiderivative, like the general antiderivative, yeah? Don't have to put it at all in these definite ones, yeah? I hope I'm not confusing you. Right, now what's this thing? Oh, we have to do that. Oh, no problem, no problem. That comes to, yeah, look, the 2 can float outside the integral sign. I'd rather put it out there and just worry about the function of x inside the integral sign. That's easy, isn't it? Yeah, it's a cinch. It's just basically 2 times 1 over the coefficient of the e to the x coefficient in the e to the x term. And it's that. And we just have to sort of clean it up a bit. Hello, Mr. Snail. How are you? Have you been slithering nicely today? It's been raining where I am, so I guess there's been plenty of Mr. Snail slithering around. So that would be that thing, wouldn't it? Yeah, it would be. Yeah. So now you've got to be a bit careful with this, because you've got to be right on your toes, because I can see an e to the 0 coming up, which is not 0. That's the point. So it's minus e to the minus 2 for when x is 1. Take away and put it in a bracket. Don't get all messed up with your signs and your double negatives, guys. Just don't be an algebra hero. Do everything one step at a time, okay? And that thing in the square bracket is going to be e to the 0 is 1. So that's going to be minus 1, which is going to be plus 1. There you go, Mr. Box. Thank you. Right. Well, we're running hot now. Let's... Oh, good heavens. Look at all this. Oh, well, come on, let's trudge through it. A, we've got that thing. That's an easy one. That's going to be a third of x cubed, isn't it? Yes, between 2 and 3 for you and me. Let's just go through it, and that gets us all that stuff. And that's just algebra, which is going to be 19 over 3, Mr. Box. Thank you. And number B. What's this one? Oh, look at this. Same integral, different x direction, going in the opposite direction. See? Now, I fell for this for the start. I started to work it out, and I thought, oh, hang on a second. This is just minus the other one. You see? Of course it is. See? There you go. So that was nice, wasn't it? They're trying to make us realise that. Okay, here comes number C now. What's that thing? Not too hard, not too hard, not too hard at all. They're mixing it up. We've got an e to the 2x with just a 1 there. We're going from 0 to 4. Mr. Snail. Thank you, Mr. Snail. Now that gets us that expression, doesn't it? Look at it, look at it. Do you agree? Yeah, that's going to get that thing there. And we are working out the whole thing. And we're going to... Oh, look at that. That's interesting, isn't it? So, yeah, we've substituted 4 in for the first bracket, and we've substituted 0 in for the second bracket. And what's that going to get us? Just don't be an algebra hero. Do it all nice and calmly and methodically, and you'll be okay. Okay. So what's that get us? 8 e to the 8 over 2 plus 7 over 2. I think it's box time. Thank you, Mr. Box. Now, we've done A, B and C. Oh, we've got D, E, F and G to go. Don't worry, we're going just fine. Where's D? What's that thing? Well, that's not so hard, is it? That's just practice in getting the integral process right. That's a polynomially one, isn't it? So, okay, you tell me now, without me doing it for you, what's the antiderivative of x to the half? What is it? Well, what's 1 more than a half? It's 3 over 2, so it's going to be 1 over 3 over 2 times x to the 3 over 2, etc. Yeah? Did you know that etc. is a Latin word which means and the rest? Isn't that interesting? Yeah, it's directly from the Latin. So that's the expression we get, guys, and let's just substitute it in, plug and play, and what do we get? We get that thing. Because the zero terms, when x is 0, of course, you just get nothing, because they're just zero terms. So that really is just amounts to subbing in when x is 1. And that comes to that, and that's going to... Now, we've got a lowest common denominator, that thing. And the quick way to do that is to kind of cross-multiply the terms. You multiply the top left 2 by the bottom right 5, and the bottom left 3 by the top right 2, and then put it all over. The denominator's multiplied. Did you know about that? It's very neat. And you get that, 16 over 15. Thank you, Mr. Box. Okay, that's D done. Hello, Mr. Snail again. Okay, he looks very happy today, probably because it's been raining. Now, E, right, for you and me. Oh, look, we've just mixed up an x to the something term with an e to the something term. They're trying to trick us, but of course they won't, because we're not going to be algebra heroes. We're going to be methodical. There it is. You see how I did it? I'm very happy to not do too many steps at once. I don't want to overload my working memory. I want to be right at the end, you see? So I put 1 over the 3 over 2 times x to the 3 over 2 plus 1 over a half times e to the x over 2. Look, that's really important, because you can go so wrong in these things if you try to do too much at once. Okay? Now I'm cleaning up, and it only took me one more line to get it right, you see? And especially in exams you do that. Alright, so let's sub in now. 4 over 3 times 4 to the 3 over 2 plus 2 times 4 over 2 minus the whole thing with 1 subbed in there. And it looks a bit messy, but hey, we can do it. Now, what's 4 to the 3 over 2? Come on, you tell me. Yes, 4 to the half is 2. 2 cubed is 8. That's right. Good work. Good work. And that's the rest of the expression. Now let's just clean it up. And we've got 28 over 3 plus 2e squared. Where did I get that 28 from? Oh, 32 over 3 minus 4 over 3. I get that. Yeah, that's fine. And that comes to that. Alright, so good work. Good work. Now, that's that one done. Now let's do F. Here comes F. It's a loggy one. Goodness, a loggy one. Now, see that, guys? Now, you see that thing there? I'm going to do that with variable substitution just to show you how to do it. I know the formula says you just go immediately 1 over the coefficient of the x term times the log of modulus 5 minus x, but I'm going to show you why, so that you'll know, because I think it's far more important to get that if you ever have to go back there, if you forget the other, standard cookbook, textbook formula, So let's u equal 5 minus x, okay? Therefore, du dx equals minus 1, and du is minus dx, okay? Now, I'm just about ready to go, but I'm just got to give you a very big warning here. You'll notice that I haven't put any limits, the limits on the integral sign, because I'm in the middle of a transition here from u to x, and the limits that you have to be putting there have to be right. They have, and it's better to only have one variable there when you're putting your limits in there. So there's a lot of students lose a lot of marks for doing that wrong. So I'm going to go over the page. I'm seeing that, just let's get this right first. I need minus dx for du, so I'm going to fix that, okay? I'm going to put a minus there and a minus out the front, and that gets me du instead of minus dx, which is really good. Now, where was I? I got that, didn't I? Okay, so I'm just going to fix it all up in terms of u, and then I'm going to put those limits back in, because you've got to be jolly careful. Okay, so that's what that is. Now I'm saying that x goes from -1 to x was plus 4. So I'm going to convert that into u's, okay? So when x is -1, u is 5 minus x, which gets me plus 6. When x is plus 4, u is 5 minus x, which is 5 minus 4, which gets me plus 1. Now I'm going back to definite integral land. Now I'm completely correct there. They can't take any marks off me. I've done it correctly. But you must not mix up your variables. If you're doing u's, you must have u's on the limits, not x's. You will lose your marks because you are wrong. It's completely wrong to write it like that. Sorry to rant. Now what I did there was I did a little trick. I said I don't like that minus out the front. I'm going to reverse the terminals and make it a plus. Ain't that neat? So we get this, and we get that, and of course log of 1 is 0, so we just get a log of 6, and Mr. Box, thank you Mr. Box, you're the man. Right, I think Mr. Snail is slithering again. Hello Mr. Snail. G, oh this is the last one, oh goody. Now, this G one, I'm just going to do it the standard way now that I've showed you the variable substitution way. Okay, this is the easy way, once you know what you're doing with variable substitution. So this thing here is going to be that. That's very easy. It's a lot less trouble than the variable substitution, isn't it? But look, you need to know what you're doing before you're just plucking formulas out of the air. That's why I did the previous one the way I did it, to show you, so that you'll see where that thing comes from out in front of the log sign, yeah? Righto, so what's that going to be? Let's do it. And this is a very interesting one because, look, we get minus a half of log of modulus of 5 minus 10. Now, goodness, 5 minus 10 is negative, is minus 5, and the modulus of minus 5 is just 5. Do you get that? Yes, and the same thing for the second term. See, modulus of 5 minus 8 is actually the modulus of minus 3, which is plus 3. And look at the double negative. So come on, don't be an algebra hero. Put it all in brackets and just worry about it later. Okay? With that minus a half, I mean. So that's what you get, guys. That's good. And let's just take that another step further. So it's going to be the log of 3 over 5. Okay? And Mr. Box is going to fix us up. I think we're finished now. Hooray! Isn't that great? Well, that was a bit of a marathon session, wasn't it? So, I hope you got it. It's a crucially important session. That's why I wanted to do a presentation for you today. Okay, thank you so much, and see you later. Bye!